This is section 4.2, number 15. There's two parts to this problem. This screencast will just talk about part A. Here's our non-homogeneous linear second-order differential equation. The non-homogeneous term is a cosine, so one of the approaches to try for the particular solution is to try a cosine 3t plus sine 3t. For the homogeneous equation, we would find the roots of the characteristic polynomial and proceed from there, but this is strictly discussion of the particular solution. Once we decide that this is the form that we're going to use, the first derivative follows and the second derivative follows. Straightforward. We take those expressions, plug them into the differential equation I'm denoting with a star. Second derivative plus 3 times the first derivative plus the function itself. Here's the second derivative plus 3 times the first derivative plus, here's the function itself, equals the right-hand side cosine 3t. Grouping the terms that have cosine 3t, I have a minus 9a, I have a 9b, positive 9b, and I have a positive a, cosine 3t. Altogether I have minus 8a's and 9b's. Those are my coefficients for cosine. Similarly for sine, I have minus 9a and minus 8b as my coefficient. Here's my minus 9b. But here's a plus b, so that gives me a minus 8b. And here's my minus 9a right here. Equating, here's a cosine 3t on the left side, cosine 3t on the right side. The coefficients have to be the same. This has a coefficient of 1, and so I say minus 8a plus 9b has to be a 1. On this side, there are no sine of t, 3t's here, so this coefficient must be a 0. Since both expressions have a minus sign in front of them, I multiplied through by minus 1 and said that 9a plus 8b must be 0. Two equations and two unknowns. We know how to do this. We find that a is negative 8 over 45 and b is positive 9 over 45. Next slide. Putting that all together, I have this is a particular solution, and this is fine. This is correct. The problem is that if I said to you, what's the amplitude, and by the way, the particular solution will also serve the role of the steady state solution, as the homogeneous solutions are damped and go to 0. This is what we're left with over time. We're left with this particular solution. So it's good to be able to say what's its amplitude and what's its period. Period is easy. It's 2 pi over 3. But its amplitude is something best seen when we rewrite this in the form of a cosine 3t minus phi, where phi is just the phase shift and a is the new amplitude. Using the trigonometric identity that the cosine of a minus b is the cosine of the first times the cosine of the second plus the sine of the first times the sine of the second. So I've got cosine phi, cosine 3t plus sine phi, sine 3t. Equating, again, the coefficient, here's a cosine 3t, and in this particular solution, it's cosine 3t. This coefficient is minus 8 over 145. This coefficient is a cosine phi. So I have this equation, and similarly, the coefficient of sine 3t in this form is a sine phi. That has to be the same as 9 over 145. Solving for a, as I did in class, the technique is to square both equations. Square this equation and square this equation. And then when you add them together, you have the nice trigonometric identity. Cosine squared phi plus sine squared phi has to be a 1. And so a squared is 145 over 145 squared, or 1 over 145. A can be plus or minus the square root of 145. Next slide. So just reminding you that on the previous slide, we had this statement that a cosine phi is negative 8 over 145, a sine phi is 9 over square root of 145, and a ended up being plus or minus the square root of 145. In general, I always use, and I recommend using, just the positive square root. But it does work in the case of the negative square root, and there is an advantage to that as well. So I'm going to show you both situations we get comparable answers. If a is a positive number, and here I am up here with my a, and I move it to this side to clean it up, I have that cosine of phi is still a negative number, negative 8 over the square root of 145. And if I take my a here and I move it to this side, dividing by a, I have that the sine of phi is 9 over the square root of 145. I want to point out that if a cosine is negative, so cosine is negative, and sine of that angle is positive, the only place for that angle to live is in quadrant 2. It's the only place where cosines are negative and sines are positive. Dividing the sine of phi by the cosine of phi gives me the tangent of phi, and I have the statement that the tangent of phi must be 9 over 8. To find phi, I take the inverse tangent, but you've got to be careful that the inverse tangent, in this case, returns a value that's in quadrant 4. The inverse tangent always returns values between pi over 2 and minus pi over 2. So this is the one tricky thing, that this expression is in quadrant 2, this expression is in quadrant 4. To move it into quadrant 2, I would add pi. And in pi, I would, by doing that, I would find in quadrant 2 a similar tangent, whose tangent of minus 9 over 8. So this angle phi also has a tangent. This is the angle phi that we need to use. So this result puts me in quadrant 4. I need to be in quadrant 2. I add pi, and this is the angle for phi that I'm going to use. Up here, you see I've put it all together. Here's my a, cosine 3t minus phi. So my amplitude of my steady state solution is this. This is the phase shift. Its period is still 2 pi over 3. However, had I said, oh, I want to use the negative square root, the negative value of amplitude, which is fine, taking that negative number and coming back over to here, dividing through by a would force this term then to be a positive. So cosine of phi would be a positive 8 over the square root of 145. And the sine of phi, if I took a negative value of a and divide through, this side becomes negative, and sine of phi would be negative 9, similar numbers. But cosine is positive, sine is negative. That only happens in quadrant 4. Still, I have to find my phi. Dividing sine of phi by cosine of phi, I get the ratio of minus 9 to 8. Inverse tangent of that gives me that phi must be negative 0.844. That is in quadrant 4. That's where phi needs to live. And so I come up here and say my amplitude is negative 1 over the square root of 145. Cosine 3t minus phi, well, phi is already negative, so it shows up as a positive 0.844. If you graph these two things in your calculator, they're identical. I prefer and I recommend sticking with one that has positive amplitude, but this is correct. Okay, good luck.